Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. For billions of years, the Earth was a sterile, volcanic wasteland, a chemical soup simmering beneath a thick, toxic atmosphere. Then, approximately 3.5 billion years ago, something extraordinary happened. Life emerged. But the transition from simple chemical building blocks to complex, self-replicating genetic material, the double helix we know as DNA, is one of the most persistent mysteries in science, known as abiogenesis. The challenge wasn't just assembling the pieces, it was keeping them intact. The primitive genetic material of early life, likely RNA, was incredibly fragile. Early Earth environments, hot, acidic, often high-pressure zones like deep-sea hydrothermal vents, were harsh. RNA needed a bodyguard, a chemical scaffold robust enough to survive the turbulent chaos, stabilize the phosphodiester backbone, and crucially, catalyze replication. We often credit elements like carbon, hydrogen, oxygen, and nitrogen. But the true, forgotten trigger, according to a groundbreaking theory, might be an overlooked element often grouped with the rare earths, scandium. Scandium, element number 21, is usually employed in aerospace alloys due to its extreme lightness and strength. On Earth's surface, it is relatively scarce. But deep within volcanic zones, its concentration can be significantly higher. Its chemical profile is what makes it so revolutionary in the context of early biology. Think about DNA or RNA replication. This process requires metallic ions acting as cofactors, like tiny molecular clamps. Today, life relies heavily on magnesium, Mg2+. Magnesium is abundant, but chemically, it has a significant drawback for an RNA-based world. It tends to bind weakly and nonspecifically, making the fragile RNA strand prone to hydrolysis, or breaking down in water. In the high heat, high-stress conditions of early Earth, magnesium was simply not up to the task. This is where scandium enters the picture. As a trivalent cation, Sc3+, scandium has a very high charge density and a relatively small ionic radius. This combination allows it to bind exceptionally strongly and specifically to the phosphate groups that form the backbone of the RNA/DNA strand. While magnesium might hold the strands loosely, scandium acts like superglue, creating a durable, chemically robust structure. Laboratory experiments simulating the RNA world have shown that in the absence of complex stabilizing proteins, Sc3+ ions are far superior to Mg2+ ions in stabilizing RNA under heat stress and driving efficient non-enzymatic replication. Scandium's unique octahedral coordination geometry provides the perfect structural support, neutralizing the negative charge of the phosphate backbone more effectively and protecting the nascent genetic code from degradation. Imagine the earliest protocells forming near a hydrothermal vent, bathed in a mineral-rich solution. These vents were natural geochemical factories, often rich in transition metals like scandium pulled from deep crustal rock. In this localized environment, any RNA molecule that managed to incorporate scandium into its structure gained an immediate and overwhelming survival advantage. It could replicate faster, survive higher temperatures, and maintain structural integrity where its magnesium-dependent neighbors would simply dissolve. Scandium became the evolutionary bottleneck, the chemical key that unlocked the stable structure required for true self-replication. It was the crucial trigger that allowed the molecular revolution to move from fleeting chemical reactions to sustained, inheritable information. So, why did life switch away from scandium? As life evolved, it moved away from harsh volcanic nurseries and developed complex protein enzymes, polymerases, which could achieve stable replication much more efficiently. These complex enzymes evolved to work with the much more abundant magnesium, which was cheaper to acquire metabolically. The legacy of scandium, however, remains hidden deep in our molecular history, a silent testament to the extreme chemical conditions that necessitated its use 3.5 billion years ago. The search for the origin of life is often a search for organic compounds. But sometimes, the true solution lies in the inorganic world, in the metals, the geological catalysts, and the rare elements that provided the necessary stability for fragile biological systems to take their first, crucial evolutionary steps. The Sc3+ ion wasn't just a helper. It was the foundation upon which the entire DNA superstructure was built. For more incredible facts like this, don't forget to subscribe and turn on notifications.